In this video I'll be talking about lessons 1 through 3 in Module 3. It's talking about exponential functions, which are a new type of function. The first lesson was talking about different types of functions, whether they're linear or exponential. We identified this first type of function as linear because the differences between the numbers were constant. Two plus 2 equals 4, 4 plus 2 equals 6, and so on. In fact, between every number, there was a jump of 2. Whereas in the second one, we had a different pattern. The pattern was not adding by 2. We had 2 times 2 gave us 4, and then 4 times 2 gave us 8, and so on. So the differences between these two patterns is one of them was an addition pattern, and one of them was a multiplication pattern. In order to understand the next part of the lesson, I want to turn to one of the last pages where we talk about exponential functions. And based on the information that we saw in the do now, we can see that exponential functions went much faster than linear functions. They started growing very fast. So you can say exponential functions grow or shrink extremely fast. An exponential function doesn't have the same form as linear functions. Linear functions often take the form y equals mx plus b. That's for a linear function. But an exponential function is y equals a times b to the x power. And the a and the b stand for different things. You can see here that the a value represents the y-intercept, and the b value represents whether it's growing or decaying. And there are several examples down here of exponential growth where this pattern is sort of starting off low and getting larger faster and faster and faster as it moves from left to right. Whereas in this example, we start off at a higher value and it's getting smaller and smaller and smaller as time goes on. That's the difference between exponential growth and exponential decay. The key to determining whether exponential is going to be growth or decay is looking at the equation. In this example that I gave to you, the equation says 1 over 2 as its pattern, as its growth or decay pattern, and you can see it's decreasing. So the thing that you should remember is if this value, which is our b value, is between 0 and 1, then it's going to be decay. If this value, which is called the b value, if it's larger than 1, then it's going to be growth. Taking a look at the examples, we can see that this example has a growth pattern. Its b value is greater than 1. So for this one, we would say it is growth. In the next example, we can see that the b value is less than 1. Since that number is less than 1, we can call this decay. For the third one, we can see that the value of b is 1.01. Well, very clever. Very close to 1, but it is larger than 1, so we call this one growth. And for the last one, the value of b is 2/3. 2/3 is smaller than 1, so we can say that it is decay. Whoops. The next piece of information we're going to look for is the y-intercept. You can see here that the y-intercept is the a value, the value that's before the growth pattern or decay pattern. In this case, the value here is 24, so our y-intercept will be 24. In the next example, we have 9 as our a value. This value, which is given to us as 9, is going to be our y-intercept. For the third one, it gives us the value of 97. Seems like a very large y-intercept, but, well, that's what they give us. So since 97 is the number that's there, we say that the y-intercept is equal to 97. And the last one is a little tricky because it doesn't actually say what the a value is. It doesn't have a value of a here. But remember from class, it's legal, mathematically speaking, to put a 1 in front of any number that you're multiplying. So you can say that this value is 1, so my y-intercept is equal to 1. So at this point, we're at the solo spot. I'd like you to pause the video briefly and try to determine whether the function is growth or decay, and state the y-intercept of the function. Try to do that now. And we'll go over the examples one at a time. In the first example, you see it's 12 times 0.4 to the x power. The y-intercept is 12 because the first value here is 12, and the second value, which is in the parentheses, is 0.4. 0.4 is less than 1, so we call it decay. In the next example, we have 30 times 0.80 to the x power. The y-intercept is 30. Of course, you could express any y-intercept as 0, 30, and you'll be fine. The decay, this function is decay because 0.80, 8/10 is less than 1. In the next example, you're given a fraction as the pattern, but 5/4 is greater than 1, so we call that growth, and the y-intercept is 8. For the last one, it was a little tricky because the y-intercept wasn't written, but as we stated before, it's legal to write a value of 1 for our y-intercept if it's not present, and the growth factor is in fact growth because 3 is larger than 1. Hope you got those right. Now, knowing that information about y equals a times b to the x, the exponential function, is really useful for every single one of these lessons. For example, in lesson 2 in the problem set, the graph is shown, which is an exponential function. You can see it's exponential because it's increasing at an exponential rate. It's starting off slow, and then it's getting faster and faster and faster. Anyway, it says using the graph complete the table below. We can see that -2, 0.5 is one of the points that they gave to us. The next point here is -2, -1, 1. So this value is 1. And I might have thrown you off a little bit because these lines all represent 1/2. They don't represent 1, they represent 1/2. 0, 2, it's right there. And then 1, 4 is the next value. Without looking at the b, c, and d, let's try to make the equation ourselves. We're looking for first the y-intercept, and we can see the y-intercept is equal to 2 in this case because that's where it hits the y-axis. The growth or decay factor, just the pattern we call it, is what's being multiplied or what's being divided here. So if you look at the jumps between these numbers, from 0.5 to 1, from 1 to 2, from 2 to 4, we can see that every time what we're actually doing is multiplying by 2. Times 2 here, times 2 here, etc. So it's fairly easy to see the pattern is going to be multiplying by 2. So if I were to write an exponential function, we would start with y equals a times b to the power of x. Now, how to write power? Oh, here it is. And we can see that the a value is going to be the y-intercept, which is 2. The b value is going to be the pattern, and everything else just gets filled in. So y equals, the first value is going to be 2 because of the y-intercept. The next value is going to be 2 because of the pattern. It's a growth pattern. And the exponent, big surprise, is just going to be x. Looking at that same lesson, which is lesson 2, example 2a and 2b from the problem set, it asks you to write an equation from each graph. All you need to do is identify 2 things. You need the y-intercept, and you need the pattern. Pause the video at this point and try to do these, and I'll give you the answers as soon as you unpause the video. Alright, the y-intercept here was 4. We identified that by simply looking at the y-axis. This point here was 0, 4. So that's how we got the y-intercept of 4. And our pattern was 2. If you weren't able to see this pattern from just looking at the graph, you needed to take the points that were given and make them into a table. And I made them into a table like this. Here we go. Here's your table. And when you look at the table, you see that the x values are always going up by 1. That's how x values should act. And the y values are increasing by a pattern of doubling or multiplying by 2. 1 to 2, 2 to 4, 4 to 8. Eventually you're going to get 8 to 16, which is up here. In any event, the pattern is 2. So we compose the function just like this. Y-intercept, pattern, and x and y stay the same for every example. Similarly here we have our y-intercept of 4, but our pattern here is 1/2. We know that it's going to be 1/2 because we're not increasing here. You can see that as we're going to left to right, this expression, or this function, is decreasing. So since it's decreasing, this number has to be smaller than 1. So since this is the pattern 1/2, you're dividing by 2 rather than multiplying by 2. That 1/2 goes right in the parentheses. No big surprise here. And 4 times 1/2 to the x power is going to be your answer. It turns out you can actually work the other way. We're given the function, which in this case is f of x equals 4 times 2 to the x power. And from that we're supposed to create a table and then create a graph. The piece of information that we're going to start with is the y-intercept, which is 4. So if I wanted to make a graph, I'd be able to make it pretty easily starting at y equals 4. But then how do I get my next number? This pattern tells me that I got to multiply by 2 in order to get my next number. So 4 times 2 is 8. So I'm going to go 1, 8. And that's my next point. Multiplying by 2 again, I get 2, 16. And multiplying by 2 again, I get 3, 32, which is somewhere up here, way too far away for me. So now that I have a couple points, I can try to join them with a smooth curve. I'll do the best I can with this computer drawing program I have here. And then after this, it's going to start tailing off just like exponentials tend to do. Arrows at the ends. And we, of course, need to label it with our equation. So we can say y equals 4 times 2 to the x power. We're also asked to create a table. I'm going to do a fairly quick table here. I'm not going to draw a box or anything like that. I'll just name the points that I named. So one of the points that I named was 0, 4. The next point that I named was 1, 8. And then after that is 2, 16. I can use a similar strategy to graph the other one. It looks like we're starting from the same value. We're given the information that the y-intercept is still 4, but our growth pattern is 1/2. And in this case, it's not really a growth pattern, it's really decay. It's smaller than 1, so it has to be decay. Starting from the first point, we'll start from 4, which is our y-intercept. And the pattern is 1/2. So in order to figure out 1/2, we just divide that number by 2, becomes 2. Divide 2 in half becomes 1. Divide 1 in half becomes 1/2. That number becomes 1/4. And then 1/8. And it's getting a little silly to try to draw these, so I'm going to stop trying to draw them and simply try to connect them with a smooth curve. That smooth curve is going to look a little bit like this. And you can tell that it's going to be essentially the mirror image of the previous graph. Well, it doesn't look so good, but hopefully you get the idea. We put arrows at the ends to represent that it extends infinitely in both directions. We'll put a label to make sure people know what the heck we're talking about. Y equals 4 times 1/2 to the power of x to the power of x. And our table is going to look very similar to the previous example. We start with 0, 4. The next value is going to be 1, 2. We determined that that was going to be 2 because we're cutting our y value in half every time. 2, 1. We could even go to 3, 0.5, or you could write 1/2. Don't be scared of fractions, kids. And the last one you can write is 4, 0.25, or 1/4, or 1/4. Alright, that's all the time I have for this video. I hope this is helpful to you. Please be aware that there will be a test coming up, more than likely next week, right before Thanksgiving.